Welcome to the pre-recording of lecture 11 of MCS 481. So in this lecture we close off our treatment of the geometric view of linear programming in two dimensions. Last time we had a disappointing cost of a square in the number of half planes. We will see that with randomization we can get a much better running time. We will also deal with unbounded linear programs. These are optimization problems where the feasible region is a polygon, a polyhedron, not bounded. But I will start by introducing the important notion of duality or polarity. So in the start of the course, we introduced a polygon as the convex hull of a point set. This week, so in chapter 4, we look at polygons as the intersection of half planes. The two views are equivalent. So we also have the convention that we can work with outward pointing normals or inward pointing normals. So here the picture, we have a simple triangle spanned by 3 points, 3 edges, although the green region, the polygon P, is cut out by 3 half planes. I have indicated the inner normals, so -1, -1, and this corresponds to the first inequality here. So you can see that the origin is inside the polygon, 0, 0 satisfies. So you can read off that the vertex most to the right is 2, 0. So you can see that 3, 0, if you go further to the right, then you have -3, and -3 is not larger than -2. So the -3, 0 point does not belong to the polygon. The other extreme is 0, 2. So these are the two vertex points that lie on this orange line, the first half plane. And then we have the vertex point -1, -1. And the two half planes have inner normals 3, -1 and -1, 3. So formally we say that all the points inside the polygon satisfy a finite set of half planes. So the coefficients of these linear inequalities, they are the vectors that are perpendicular to the lines. They are oriented inward. For that reason, our inequalities are larger than or equal. And the right-hand side, the offset, is actually can be computed as the minimum that all these the minimum that can be obtained by taking the inner product with the coordinates of the normal with any point inside the polygon. Okay, there is the dual way of looking it. So we saw this when we were using the construction of the convex hull via SciPy, which wraps Q hull. We can not only get the ordering of the vertices, but we also get the equations. So can we go backwards? So given the equations, can we go to a polygon? Can we compute the vertices of the polygon? And yes, indeed, we can. So here we have the 3 half planes, and we can with every half plane, we can associate one point. So what we do is we normalize, we take the coordinates of the vectors and we normalize them dividing by the offset. Here it's the minus of the offset. So you see that with every normal in the picture of the triangle to the left, so we have the normal minus 1, and to that normal corresponds the point minus 1/2, minus 1/2, also colored in orange. We have the normal 3 minus 1, with that corresponds the point 3/2 minus 1/2. So this is the blue point. And then we have the purple minus 1, 3 inner normal, and to that corresponds the point minus 1/2, 3/2. So the normals in the original green polygon become the vertices in the red polygon. The points of the original polygon become the normals of the red dual polygon. So we started out with the points 2, 0, 0, 2. So we see the inner normals 1, 0, 0, 1. And we had the point minus 1, minus 1, and this corresponds to the normal minus 1, minus 1. So there is this shift that is happening. So any inequality is only determined up to a constant factor. So here everything was divided by 2 in the coordinates of the vertices, but it could have been scaled. So there is some kind of normalization that takes place. Okay, so this is an important concept. So the dual of the dual is actually the original polygon. So you can read this picture from left to right or from right to left. So there is the dual correspondence between points and normals, between normals and points. All right, this is an important construction and one needs to reflect on that a little bit. Does this construction always work? Yes, provided that the origin, the 0, 0 point, is in the interior of the polygon. So, and this can always be satisfied. So you can always compute the center, the average of all the vertices of the polygon, and shift your coordinate system. So the exercise 1 is therefore solved. We can also define the dual for outward pointing normals. So do this for the construction on the previous slide. So instead of working with inward pointing normals, work with outward pointing normals. Then the convention is that you don't divide by minus b, but you divide simply by b. So again, the origin needs to be in there. But you can play the same construction. You can construct the same dual polygon via working with the other convention, working with outward pointing normals. And then in some sense this is also a computer science class. So in the previous lecture Jupyter notebooks were posted that actually constructed the equations, also constructed the drew with matplotlib the vectors. Well, extend the Jupyter notebook that is posted and construct the dual of a random polygon with 10 points. So this is so the illustration, you can still do this actually by hand, but strongly recommended that you will do this via a computer program. You will already get credit for systematically describing all the steps. So the critical step is that you will shift the points. So if you generate a random polygon with all its coordinates positive, then the origin won't be part of the strict interior. So you have to compute and you have to shift. And whenever you define an algorithm, if you can define it properly in Python, then that resolves all the unambiguity. So it's no longer, I'm sorry, it resolves the ambiguity that may come from pseudocode. Okay, the exercises are important because the notion of duality is an important concept. So this also kind of explains why you typically have the convex hull only in one direction. Because with the notion of duality, you can actually solve the other problem as well. So you can go from right to left. Okay, so let us come back to our geometric view of our linear programming problem. So in the previous lecture, we were considering a sequence of half planes. So here in the example, we have 7 half planes. And our objective is here written or drawn by this red vector. So we look for the rightmost point that satisfies all the half planes. And the half planes actually cut out this cone. So after 7 steps, we have arrived at the vertex 7. And you can see that this is an unlucky order because the optimal vertex each time goes down, each time needs to be changed, and we computed the optimal vertex as a result of a one-dimensional linear program. So, and the number of steps that you need to take is proportional. The number of steps in solving the one-dimensional linear program is proportional to the number of half planes. So adding this all up with this unfortunate order, we have a quadratic cost. Quadratic, so n is here the number of half planes. And this is very unfortunate because we know we could actually solve the two-dimensional linear programming problem by constructing a convex hull, and that works in n log n. And then it's just a linear ordering of all the vertex points, order them corresponding to their value at the objective. Okay, so here is then the new algorithm. The new algorithm constructs a random permutation on n elements and gives that as the input of our bounded two-dimensional linear programming problem. So here is the idea. Why is this going to work? Well, there are n factorial permutations, so that's a huge number. And we expect actually, so this is kind of here the expectation, we expect that the bad cases are actually relatively few in number, relatively few to the total number of permutations. So that's kind of the idea why it works. Of course, generating a random permutation, how do you do this? Well, there is an algorithm in the textbook. I can tell the algorithm in a loop, you generate n random integers between 1 and n, and you swap the current element with that randomly generated index. So that is the algorithm that is used in the textbook to generate a random permutation. And that solves exercise 4. Okay, if we work with random algorithms, the analysis of the running time takes more care. And in some sense, the linear programming that we will consider is actually too small to be really relevant. But the main point, or there were two main points of the lecture. We passed already the duality or the polar form of a polygon. The next important thing is the analysis of the expected running time. So, we have the expected cost. So the cost of the point. So if we have our one-dimensional linear programming, then the expected cost, it's either proportional to the number of hyperplanes if the new half plane makes a cut in the feasible region in a way that causes the optimal vertex to change. So we may be in the fortunate situation where the current optimum already satisfies the new added hyperplane, the new added half plane. In that sense, there is no cost. So that's why we have a 0, 1. So this expectation is the probability that the next half plane actually does not change the current optimum. Okay, and we showed last time if actually the current optimal vertex does not belong to the new half plane, then the feasible region changes. And then we solve a one-dimensional linear programming problem that takes as many steps as the number of half planes. Okay, so this is the important formula here. Okay, so how do we do this? We will do some backward analysis. So we'll actually say that the expectation that the current optimum does not satisfy the new half plane is 2 over I. So, and we will work backwards. Okay, what is the probability at the very end of the algorithm that the last vertex was actually different from the previous one? Well, we need to have at least 2 hyperplanes. So this is where the numerator comes in. The denominator comes in if we have the selection. So what is the possibility of any of these half planes? Well, it's 1 over n. And this gives us this 2 over n. And we repeat this, so we think backwards. So it's kind of an induction that runs backwards. So the probability that the half plane actually cuts off or that actually the new half plane passes through this new current optimum is actually at most 2 over I. So that's the bad case where we have to solve a one-dimensional linear program. So this expectation is 2 over I, and this reduces the cost to a linear cost. So we have actually a constant. So we are, so I should probably go back. We have this formula here. So we have something of the order that is I, but then we divide by I, and 2 is a constant. So the expected cost is of the order n. So that's the point. Okay, and that is essentially it. So this backward analysis makes that our randomized two-dimensional linear programming problem can be solved in an incremental way in a linear cost. Linear in the size of the input, the total number of half planes. Okay, so one issue that needs to be resolved. The way we resolved it, we made any linear program bounded by working with orthogonal edges. And that's kind of, well, it worked. So you could say, well, it's very equivalent to when you plot something, you choose your viewing window. But um, it's kind of arbitrary that how large should this wedges be. So we will take another view. So we say that a program is unbounded if there is one ray that is entirely inside the feasible region. And actually, if the objective also keeps increasing. So here you see the ray inside the feasible region. So the polygon is actually a polyhedron. So I only shaded um, part of, I didn't actually shade everything, but you should imagine that the green region stretches on in the direction of this blue ray D. And you see that the inner product of the red C, the objective, with the ray D is actually positive. So as you keep on going to the right, you also go up. That's one way to see this. So this is a characterization of an unbounded linear program. So this also motivates the working with inward pointing normals. So which convention you choose, maximum or minimum, maximum is outward pointing normals, minimum is inward pointing normals. From the perspective of the representation of the polygon, it doesn't really matter. But here to deal with polyhedra that are unbounded, the inward pointing normals is actually a little bit more convenient to work with. So we have our array that lies entirely inside the polyhedron. And you see, if we compare the orientations, in particular the objective C that's now pointing upwards with the blue ray D, then we see that the characterization can be quickly verified with an inner product. Okay, so here we have the inner normal. So we can I worked with inner normals with the larger than or equal, but you can always flip signs. So inner normal, outer normal. So if you have an outer normal, so ax, ay, then the inner normal is the -1. So you can also always work with less than or equal inequalities. So, and here the lemma is actually the observation that I made before. So this gives the criterion for the ray. So we have an unbounded linear programming if we have two conditions. So for all inner normals, the inner product with this ray is positive. If this would not be a case, then the blue ray would face an obstruction. But you could now say that because of this inner product that is positive, the blue ray, you can keep on walking along the blue ray and you will never face an obstruction from any of the other half planes. So there is such a ray. In some sense, you start actually with this. So the conditions 1 and 2 may be interpreted or should be read perhaps in the alternative order. So it's important that you have such a ray. And that this ray indeed makes also the inner product positive with the objective. Okay, this gives a criterion that characterizes an unbounded linear program. Okay, so here is the criterion. So let's prove it. So we have the if and only if. So if it is unbounded, and that was actually following the definition. So then unbounded means that there is a ray. If you walk along that ray, you keep on increasing your objective value, so you stay inside the polygon, and that's the first criterion. And also you don't face any obstruction. So that is following the definition. Okay, now let's work the other way. Now, if we have these conditions here, there is this ray. So actually the feasible region is actually not empty. So the problem is feasible. So actually we have a point inside the polygon. And then we apply the linearity. So we're going to, starting at any point in the polygon, we're going to walk on the direction of this polygon. And we see what happens with the change in the objective function. So we exploit the linearity of this product here. And we see that if we are working in the positive direction, so our lambda is a positive value, so we stretch it to infinity, it keeps on increasing. And we also will not face an obstruction. So because of the positive inner product, so we start out with a feasible point. So we have this inequality here that we verify. The point is feasible, so that's because that's the reason why this satisfies this inequality. And we have the condition, so we're reading the lemma from right to left, we have the condition that any inner normal, a normal to any half plane or to any line that defines the half plane, does not cause an obstruction for the ray D. So we will stay inside the polyhedron. So this also indicates the unboundedness. So we can walk till infinity, till lambda is infinity. Okay, that proves the criterion. All right. So we have therefore a way to check whether a program is unbounded or not. But we can do a lot better. So here you see now what are the candidates for the race. The candidates for the race would actually be all the facet norm, or all the edge normals. So and each time we would need to verify whether every edge normal makes actually a positive inner product with any other edge normal. So we can do better. So we can do better, in some sense this was already a little bit suggested, if our objective is actually the vertical upward pointing normal, and we can always do this by orienting our polygon in such a way that the coordinate axis is, or we change coordinates, that the coordinate axis is parallel to the objective. And then actually we do have a linear program. So actually we do have a linear program in one dimension. And that is actually that we can show that if there is, um, if it is infeasible, then actually we should have two half lines which have an empty intersection. So these are actually certificates to show that there will be an obstruction. So we will actually have um, a problem that is bounded. Okay, so I copied this from reading the textbook. And there should have been a picture here, and that is your exercise. So the book actually provides pictures. So in some sense, I might have been in a hurry when I prepared this first. So the last exercise is actually to make an example of an unbounded linear programming and to demonstrate how you can verify that in linear time by solving a one-dimensional linear programming problem. You may assume here for this exercise that the objective is already the 0, 1 vector. So we have already done our coordinate change. Okay, so now we have the general algorithm. So we will check first whether the problem is unbounded or not. If the problem is unbounded, then actually the value of the optimum is infinity. So we look for the optimal vertex. Well, actually, we have the ray that is unbounded. Otherwise, if we have an infeasible problem, then actually we also actually will provide a certificate um, that for the half planes that are infeasible. And that will come up as we run our incremental algorithm. At some point, if our polygon becomes empty, then actually we will indicate at which hyperplane this happened. Okay, so there is this pre-processing that happens in linear time that actually will indicate that the problem is actually either infeasible or it is unbounded. Okay, so that is essentially it. So we can solve two-dimensional linear programming problems in an incremental way. In linear time, expected time, and also the worst case of the storage is actually linear in the number of half planes. So that is the main result of this chapter. So I still have 15 minutes left in some sense. So I will not stretch time too much. So what I should point out is my source for the first. So my source for the duality is this book here. So it's a graduate textbook. So in some sense, if you're not a graduate student, then you can you're safe to ignore this. So what is on the slides should be sufficient. If not, if you are a graduate student, so you should actually read the introductory chapters of this textbook. This is a textbook on polytopes. So in this course, we are mainly restricted by algorithms in the plane. but the textbook of that mentioned is here takes it way farther. Okay, I have no Jupyter notebook posted for this lecture. That may still happen if I still find time. But the third exercise invites you to do this. So extending once more the Jupyter notebook of the previous lecture. The goal of this course is that you get familiar with reading the textbook. So the exercises 13, 15, and 16 are recommended. I may collect them at some later point. We close off chapter 4. So there are sections that are marked with a star. So there is the linear programming in any dimension. That gets dominated by the numerical linear algebra. So there is a pivoting process that is taking place, swapping out, swapping in constraints, going from vertex to vertex. A very important result, and this is again talking to graduate students, is that the linear programming problem can be solved in randomized linear time. If you randomize, then it's also linear in the number of constraints. And that was an important problem because you could cycle if you hop from vertex to vertex. There are variations on the linear programming problems. This could also be, if you read the textbook and you see that the sections that we have not covered, that they are very interesting to you, that could be a topic for a final project in this course. Okay, so this lecture perhaps went a little bit too fast. I hope you paused a little bit with the construction of the dual of a polygon. Günther Ziegler prefers the polar construction of a polygon. So that is one important concept. The analysis of the randomized algorithm with the backward looking, but the backward analysis is also an important idea here. Perhaps also that may have gotten a little bit too fast. The inward pointing normals are actually good to work with unbounded polyhedra. And we actually gave a criterion. The criterion was developed for polygons for polyhedra in the plane. But I hope it's clear that the construction extends to space as well. Okay, I'm close to 40 minutes in this 50-minute time slot. I will not drag on much longer. In the actual lecture, there will be much more to talk about.